In this video, we're going to cover the structure and properties of carboxylic acids and how they act as weak acids, the structure and properties of esters, how they are formed and how they are named, and the hydrolysis of esters, looking at acid and base hydrolysis, what fats and oils are, and what biodiesel is. We're going to start off by looking at carboxylic acids. Carboxylic acids have the COOH functional group, which you can see drawn out here. They are named using the suffix oic acid. You don't need to give the number of the carbon in the carbon chain for a carboxylic acid. It will always be carbon 1, as the carboxylic acid is always at the end of the molecule. So, for example, for propanoic acid, these would be 2 different ways to represent it, each of these having 3 carbons in the chain. You may be asked to draw or name some slightly more complicated carboxylic acids, for example, 4-hydroxy-2-methyl-butanoic acid. Again, here you can see we've got 4 carbons in the chain of each of these molecules. The hydroxy, or the alcohol group on carbon 4, is carbon 4 at the left-hand side because the carboxylic acid group will be carbon 1 in each case. As we've already got the suffix oic acid for the carboxylic acid, we'll use the prefix hydroxy for the alcohol group, and we've got a methyl group on carbon 2. Carboxylic acids are weak acids, and this is because they only partially dissociate in water. You can see here an example of that dissociation equation. Given they only partially dissociate, we draw this using an equilibrium sign, and the equilibrium for the reaction will be far to the left-hand side. So you'll only have a small proportion of the dissociated acid on the right-hand side. In comparison, a strong acid would fully dissociate. So something like hydrochloric acid or a general strong acid HX would fully dissociate into the hydrogen ion and your associated anion. Again, because this is a fully dissociated reaction, we've used a normal arrow as opposed to the equilibrium we use to represent the partially dissociated weak acid. Carboxylic acids will react with carbonate ions, the CO3 2- ion. When they react with carbonates, they'll form a salt, carbon dioxide, and water. So for example, we'll look at the reaction of ethanoic acid with sodium carbonate. This would form sodium ethanoate, carbon dioxide, and water. So O8 is the salt you'd get from ethanoic acid. So we've got the metal of sodium, so it would form sodium ethanoate. If we had methanoic acid, for example, that would be sodium methanoate. If it was propanoic acid, it would be sodium propanoate. You need to be able to write and balance symbol equations for these reactions as well. In this case, we know the carbonate ion is CO3 2-, therefore we must have 2 sodiums to balance out that charge, and it's just a case of writing the associated correct formulas and then balancing at the end. If you need more practice on this, look back in the work on balancing and writing equations you did in the physical chemistry topics. We'll look at a second example, this case in reacting carboxylic acids with hydrogen carbonates. So if we look at the reaction of methanoic acid with sodium hydrogen carbonate, this should produce exactly the same types of products, a salt, carbon dioxide, and water. So in this case, we'd produce sodium methanoate, carbon dioxide, and water. And again, we'd need to be able to write a simple equation for this. The only difference this time is that the hydrogen carbonate has got HCO3, so essentially it is HCO3 1-, so we'd only need one sodium to balance out that charge. It makes the equation a little bit simpler as there are no big numbers needed to balance the equation, unlike when we were just using sodium carbonate. We're now going to look at the structure of esters. This is a new type of functional group you've probably not come across before. This is the functional group of an ester. You've got a carbon chain attached to a carbon, double bonded to an oxygen, another oxygen bridging the first part of the molecule to a second carbon chain. We've used R and R' to represent the two carbon chains. R' just means it can be a different length carbon chain to the first R over here. So for example, you could have 5 carbons being represented by the first R and 10 carbons represented by the second R. If this little apostrophe wasn't up here, the R's would be the same, so therefore if the first R was 5 carbons, the second one would also have to be 5 carbons. That's just what the little apostrophe represents up here. We'll look at this in more detail when we look at how to name these molecules, but it's important to recognise that these 2 carbons are on the first part of the molecule and this 1 carbon is on the second part of the molecule. So there would be 2 carbons in total here, not just the 1 carbon to the left. So we count both of these carbons together with 1 carbon over here. This is another example of an ester. We've got 3 carbons in the first part of the molecule and 1 carbon in the second part of the molecule. If you heat a carboxylic acid with an alcohol in the presence of a strong acid catalyst, usually sulfuric acid, you'll produce an ester. We call this an esterification reaction. This is the general equation for an esterification reaction. The carboxylic acid will react with the alcohol using a strong acid catalyst under reflux conditions to produce the ester and water. This reaction is an equilibrium reaction. This is the structural formula for the equation we've just written out. This is why we made a point of noticing earlier on that the R group and the R' group can be different. If we have a look at our ester here, we can clearly see how it's formed of the carboxylic part of the molecule and the alcohol part of the molecule. So whatever is attached to the carboxylic acid will be on the top left of the molecule, whatever is attached to the alcohol will be on the bottom right. So we'll look at some examples of how to form and name these esters now. An ester is named using parts of the names from the alcohol and the carboxylic acid from which it was formed. The alcohol group gives the first part of the name. This forms what we call the alkyl group of the ester. So for example, if propanol was used, that would give the alkyl group down here the name propyl. If it was methanol, it would be methyl. The carboxylic acid forms the last part of the name. You substitute oic acid for O8. So for example, if we used butanoic acid, it would give us the name butanoate. We then put both parts of these names together to name the ester. So for example, if we had propanol and butanoic acid reacting together to form an ester, we would make something called propyl butanoate. We'd name the alkyl group first, and then the name which came from the carboxylic acid. We're now going to look at 3 examples of how to name esters. So to start off with, we'll look at what you do if you're going to react propanoic acid with ethanol. We'll start off by drawing both of these molecules out. So we've drawn propanoic acid with 3 carbons and ethanol with 2. I've drawn the ethanol this way around because this is where we're going to form essentially the bridge between the oxygen and the alkyl chain. So it makes it easier to join the two parts together when you draw the structure of the ester if you draw them in this order here. So this would be the structure of our ester. This reaction is a condensation reaction. It produces water as an additional molecule. You can see how we could lose a water molecule here to essentially join the gap between them. So this would be the structure of our ester. The first part of the name comes from the alcohol, the alkyl group, so we'll look at that first. In this case, we used ethanol. We've got 2 carbons in our alkyl group, so that will give the part of the name ethyl. The second part of the name comes from the carboxylic acid. In this case, we used propanoic acid. There are 3 carbons in the first part of the chain, so that will give the name propanoate. If we put these two together, the name of this ester overall would be ethyl propanoate. In this example, we've been given an ester and we'll need to determine what its name is. We'll start by looking at the alkyl group on the ester. The name of this alkyl group is 1-methylpropyl. Propyl, because there are 3 carbons in the chain attached to the oxygen. 1-methyl, because on that chain of carbons attached to the oxygen, there is a methyl group on carbon 1. Carbon 1 is always the carbon attached to the oxygen. So this has to be carbon 1, therefore the longest chain is 1, 2, 3. Therefore propyl with a methyl group on carbon 1. We can't name this as any kind of butyl, for example, a chain of 4, because carbon 1 in that case would be here or here, and carbon 1 has to be the carbon attached to the oxygen. So this group here is 1-methylpropyl. The second part of the name will then come from what was the carboxylic acid. In this case, there is just 1 carbon in this part of the molecule, so this would be methanoate. So putting both parts of the name together would give us 1-methylpropyl methanoate. If we wanted to, this could be a different kind of question you could be asked, we could look at what 2 molecules form that ester. So 1-methylpropyl would have come from butan-2-ol. Now that doesn't seem quite intuitive, but let's have a look at why. It's quite easy to figure out what 2 molecules will have made this ester. If we look at this part of the molecule attached to the oxygen, we know this part of the molecule came from the alcohol, so we can just change the O into an OH to draw the alcohol we would have started off with. If we look at this alcohol, there is no rule saying the OH group has to be on carbon 1, that's just for an ester, so we could then name this molecule like we normally would. Identify the longest chain, in this case the longest chain is 4, with the alcohol group on carbon 2, so this would have come from butan-2-ol. This is why it's important to draw the structure of the ester, or the structure of the molecules it was made from, when you're trying to name these. It's not as obvious as just looking at, for example, butan-2-ol and saying, oh well that must be butyl then. You've got to draw it out and name what you are given, but the names of the carboxylic acid or the alcohol can be a good starting point. In this case, the left-hand side of the molecule is quite straightforward. It's just 1 carbon, therefore it will have been methanoic acid. Again, in this example, we've got another ester which we need to name. We'll start as usual by looking at the alkyl group first. In this case, the alkyl group has just got 2 carbons, so it must be named ethyl. We'll now look at the part of the molecule which will come from the carboxylic acid. We can see there are 4 carbons in the longest chain, with a methyl group on carbon 2. This means the part of the name from this part of the molecule will be 2-methyl butanoate. 4 carbons in the chain, a methyl group on carbon 2. Putting both parts of the name together will give us ethyl 2-methyl butanoate. Again, if we wanted to, we could look at what two molecules will have made ethyl 2-methyl butanoate. The ethyl group must have come from ethanol, and the 2-methyl butanoate will have come from 2-methyl butanoic acid. A little bit more straightforward to name than the example we looked at a moment ago. We're now going to look at the hydrolysis of esters, the different types of hydrolysis, and the products each of those form. Hydrolysis is where a substance is split apart by water. In this case, it is just the reverse of the esterification reaction. We can see here how that to form the ester, the carboxylic acid and the alcohol react together to form the ester and water, but as this is an equilibrium, we could go the other way, the reverse reaction, by reacting the ester with water. That would be hydrolysis. Using water alone is a very slow process, however, so we will catalyse the reaction, we will speed it up by using either an acid or an alkali, and these are the two types of hydrolysis we're going to look at. Acid hydrolysis is quite simply the reverse of esterification. We react the ester and water together to form the carboxylic acid and the alcohol. The ester is refluxed with dilute acid, typically hydrochloric acid or sulfuric acid. As the reaction is reversible, lots of water will be needed to push the equilibrium far to the right to ensure a high yield of products. Base hydrolysis splits the ester up into a carboxylate ion, which we'll look at in a second, and into the alcohol. Like with acid hydrolysis, it'll be carried out under reflux conditions, but this time it'll form the carboxylate ion. That is just a deprotonated carboxylic acid. We'll now look at an example of what the equation would be if we were to take base hydrolysis and apply it to the ester methyl ethanoate. So we can see how the equation is very similar to the generic one we've given above. We'd add the reflux onto the arrow, and this would be the carboxylate ion which we would form. So if we were hydrolyzing methyl ethanoate, we can see here we've got two carbons joined onto the double bond oxygen. That must mean we would have had ethanoic acid at some point, so our carboxylate ion would be ethanoic acid but deprotonated. So we would call it ethanoate. We'd also form the methanol as well. Esters have a variety of different uses depending on their chain lengths. They are used in perfumes and as flavourings in various foods, mainly sweets and drink products. They are polar liquids, so lots of organic compounds will dissolve in them. They also have low boiling points, so they evaporate quite easily. This makes them good solvents in glues and printer inks. They are also used as plasticizers. They're added to plastics during the polymerization process to make them more flexible. Over time, these plasticizer molecules will escape and the plastic will become more brittle and stiff. So what we call fats, animal fats and vegetable oils, are actually esters of glycerol and fatty acids. Glycerol is a chemical called propane 1,2,3 triol, and we'll look at the structure of that in a second. And fatty acids are just long-chain carboxylic acids, so a carboxylic acid with a very long carbon chain coming off it. These fatty acids can be saturated, so where there are no double bonds in the long carboxylic acid chain, or unsaturated, where there are double bonds in the chain, and these give the fats or the oils their properties. This is glycerol, propane, 3 carbons, 1, 2, 3 triol. And this is the fatty acid, a long chain carboxylic acid. We're going to do an esterification reaction between the carboxylic acid and the triol, because remember, we've just said that fats and oils are esters made from the glycerol and the fatty acid. So if we've got 3 alcohol groups here, we're going to need 3 carboxylic fatty acids. Hopefully now you can see how we could join these 3 molecules to the glycerol. So each of these fatty acid chains will form an ester linkage with one of the alcohol points. And this is what our fat or oil would look like. We've made an ester between the fatty acid and the glycerol. We typically call these triesters. You can see we've got 2 chains which have got no double bonds and 1 chain which has got double bonds. You could have any combination of these in your fat or oil. We're now going to look at the properties of fats. Fats mainly have saturated hydrocarbon chains, so we can see there are no double bonds in this fat molecule. This area here represents the glycerol part, and these are the fatty acid chains. We say the chains are saturated because they have no double bonds in them. Because the chains don't have any double bonds, the chains will fit neatly together, so we can stack the molecules quite nicely on top of them. Since the molecules fit nicely together, they're nice and close, this means we're going to have strong van der Waals forces between the different fat molecules. If we've got more or stronger van der Waals forces between the different fat molecules, this means they're going to have higher melting points and therefore be a solid at room temperature. So that's why our saturated fats are typically a solid at room temperature. We're now going to compare those properties of fats with the properties of oils. Again, we can see we've got our hydrocarbon chains and our glycerol area at the front. Oils have got unsaturated hydrocarbon chains. This means that there are double bonds in those chains. The double bonds cause the chains to bend a bit, so you can see they're not in straight, neat lines like the saturated chains were. This means that the chains aren't going to allow different fat molecules, in this case oil molecules, to fit neatly together. They can't fit close together, therefore we're going to be able to not pack them as close, therefore we're going to have decreasing strength of van der Waals forces. This means that we're going to have lower melting points if we've got weaker forces. Therefore, oils are going to be liquid at room temperature, unlike fats which were solid at room temperature. So our fats and oils are just triesters. Given that they are just esters, we can hydrolyse them just like we would any other ester. So fats and oils can be hydrolyzed by heating with dilute sodium hydroxide. This will form an alcohol and a carboxylate salt, like we just looked at earlier in this video. And it's these carboxylate salts from the hydrolysis of these fats and oils which were historically used as soaps, is where the name comes from. We'll now look at an example of this process. So here we have our fat, a triester. I've shortened the chains and you can clearly see how there are 3 ester linkages here. We're going to hydrolyse it by reacting it with sodium hydroxide. we've got to hydrolyse 3 separate chains, so we will need 3 molecules of sodium hydroxide to hydrolyse it. The hydrolysis process will produce the alcohol and the carboxylate salt, so we will produce glycerol again. And our carboxylate salt is the deprotonated carboxylic acids. As we used sodium hydroxide, we're going to form sodium salts. So where the carboxylic acid has been deprotonated, the O- will be stabilised by an Na+. You need to remember we're going to form 3 of these because we hydrolysed all 3 chains of the triester. If we wanted to, we can convert the soap back into the carboxylic acid by adding hydrogen ions from an acid, and that'll displace the sodium ions, reforming the carboxylic acid. So for example, if we took one of those soaps, one of those carboxylate salts we looked at a moment ago, reacted it with H+, we would reform the carboxylic acid and leave the sodium ion by itself. Biodiesel is a mixture of methyl esters of long-chain fatty acids. So if we can get a long-chain fatty acid and convert it into an ester, we can use that as biodiesel. The reason why we do this is that we can make fuel from oils. So vegetable oils, for example, rapeseed oil, will make good fuel, but it can't be combusted directly in a car engine. It needs to be converted to biodiesel first, these methyl esters of long-chain fatty acids. In order to form these methyl esters of long-chain fatty acids, we take the oil, we react it with methanol, because we want to form methyl esters, and we need to use a strong acid catalyst, typically sodium hydroxide or potassium hydroxide, and that will form the biodiesel. So if we started off with our oil, our triester, so we've got our long fatty acid chains, our ester linkages, and we can see where we started off with the glycerol, we can react this with potassium hydroxide to form methyl esters. Again, we're going to be hydrolysing all 3 chains, so we'll need 3 equivalents of methanol. Using that potassium hydroxide catalyst, this process will form glycerol, so we'll reform the alcohol we started with, and give us 3 methyl esters. Essentially, this process does the hydrolysis of the chains, forming the carboxylate salts like we've just looked at, and the glycerol, and the carboxylate salt is then undergone an esterification reaction with the methanol to form the methyl ester. So the long parts of the chain here are present here, and the methanol group is where this side group comes from here. We're now going to evaluate whether biodiesel is actually carbon neutral. You can argue that biodiesel is actually carbon neutral because all of the carbon dioxide absorbed by the crops is exactly the same amount of carbon dioxide which will be produced when they are burnt. Therefore, being carbon neutral, the carbon dioxide coming in equals the carbon dioxide going out. However, a lot of energy is used in the process of producing the biodiesel, which isn't considered. Fertiliser is needed to grow the crops, and the carbon dioxide used to produce that fertiliser isn't taken into consideration. Neither is the carbon dioxide produced by the equipment used to plant the vegetable oils or the rapeseed oil, or to harvest it, or to convert it into biodiesel. or to then transport the biodiesel to petrol stations to be put into cars. So you've got to be able to argue both sides of whether biodiesel is carbon neutral or not.